you ever wondered why forces are crap?
So as physicists, we know what to do with it.
Have you ever wondered why forces are difficult? Welcome to Crash Course.
Free body diagrams. In order to understand forces, you need to understand Newton's law of motion. Newton's first law is an object in motion tends to stay in motion unless acted upon by another force. In this lovely diagram, we have two balls. One ball just keeps on rolling. There is no wall to stop it. The second ball will eventually hit the wall, making it stop because the force of the wall stopped the force of the ball. Newton's second law of motion. Acceleration is directly proportional to the net force, and mass is inversely proportional. So, these lovely equations that you'll need to know later on in this unit. If you increase either mass or acceleration, force will increase too. Newton's third law of motion. If you punch a wall, the wall will punch you back. Well, actually, will hit you back with the same amount of force that you put in. Allow me to demonstrate. It stopped my hand, and I'm not moving forward, and it hit me back.
Free body diagram. Since this is the force unit, there are multiple types of forces. The first force we have is just a block falling. Yay! This is the mass of the block and the gravity that is applied to it. I don't say the gravity of Earth because it could be on a different planet. Please make sure that when you are doing a problem like this, you know whether or not it's on Earth. That is very important. Now, this is where things get complicated. I'm going to be adding in the second force. It is now sitting on the ground. And the second force will be normal force. Now these two forces counteract each other because this force makes sure that the block doesn't compress on itself. Normal force is acting on anything that is standing on the ground. So it's acting on me. I hope it's acting on you. Yeah. Next, we have force applied. This can come in many forms. It can be tension, it can be pushing. All that you have to know is that this is the force that will be, it has to be manually applied to the object. Now, sometimes the force can be somewhat in the y direction. In that case, you'd have to use a lot of math to figure out what normal force is. But in this case, it's just completely in the x direction. Now, the last force, and probably the most important force, is the force of friction, which doesn't exactly counteract force applied, but it does slow down the object when you are pushing it or when it's having something else applied to it. Now, to the next section. The best way to learn about ramps is to do a problem for yourself. So the first step is always to identify whether you need to use the x or y axis or both. So our question here is, how much force is needed to keep this 8.0 kilogram block stationary? So as you can see, if we keep our x and y like this, it would be a very difficult problem to solve. So rather than keep it like this, we are going to turn it into this. So that way we only have to change this one with sine and cosine. The next step is to identify which one to use and what they will equal. So since it says stationary, we will say that this is 0 and this is 0. And since our x-axis is this, we will not be using the y-axis. So now that we've identified which axis we are using, we should identify which angle we are using right here. Now, an easy trick is to do this. Draw a complete triangle like this. Make sure it has a 90-degree angle, because basically what you're saying is that this angle is the same as this 54 degrees over here. And if you say that, then this angle is also the same as these 54 degrees down here. Now, after you identify that, you need to draw your free body diagram, which Thought Bubble has so graciously already done for us. He has also given us our variables. But more importantly, we have to identify what kind of equation we need to use. So the most common equation used in these problems is mg sine theta. Now we use sine instead of cosine because the triangles, as exhibited over here, are flipped. But yes, we use sine. So now that we've identified that we are looking out to get this horizontal force to counteract this force, we know that our equation is going to look like this. Because beforehand, like this. So we know that these two equal each other. So real quick, with magic, I'm going to write these down. So the answer is this. 63 newtons is equal to the horizontal force that we would move to keep this block stationary. And as you can see, I wrote it here where the problem originally was, with its units. Do not forget the units. Or your free body diagrams. Free body diagrams. And remember, if you don't know whether or not to use the x-axis or the y-axis, it is perfectly fine to use both. Just remember that you can change your x and y axis to fit the needs of the diagram. Free body diagrams.
There are two different types of friction found within this unit, kinetic and static. So, what if you have no idea if the object has kinetic or static friction? Well, is the object sliding on the rim? If it is, then it's kinetic because, it's moving. But if it isn't, then it's static. Well, let's say you have absolutely no idea whether it's moving or not. Then come down here and answer the question, is the net force applied greater than the maximum static friction? If the answer is yes, then it's kinetic because then the force applied will cause it to move. But if not, then it's static because the force of friction is going to be greater than the force applied.
Personal words.
Oh. It's recording now. Okay. Kepler's laws. The first law is planets move in elliptical orbits with the sun as the foci, which is the center. Sun. They move. Okay. The second law is a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. So, equal areas in equal time. Okay. Third law. The square of the orbital period is proportional to the cube of their mean distances to the sun. Another definition is gravitationally attractive. That is the force of attraction between all masses in the universe. And to become more attractive, you must either increase your mass or decrease your distance between the two masses. The equation for gravitationally attractive is the absolute value of the force of gravitation equals gravity's constant, which is whatever the acceleration due to gravity is on that planet, times the mass of object 1 times the mass of object 2 divided by the radius squared.
It is speed reading time with me, Chloe. Now, we will be focusing on tension, more specifically, Atwood's machine. Basically, we're just going to go through and identify what each variable is since we don't have enough time to actually do an equation. So, this is our lovely equation for Atwood's machine. We have mass 1, mass 2, gravity, and acceleration. All of these things, of course, can be applied to the diagram, but one of the more important things is that the tension right here and the tension right here are equal. Do not forget, they are equal. Also, one last thing, free body diagrams. Thank you, good night.
Free body diagram!
And that's all for Crash Course.
See you next.
Free body diagram.
Diagram. What is this diagram? Acceleration will increase also.
One of the two will increase.
Yeah, okay.
It's just, yeah.
Is that the same video?
Is it still on? Good, great. We will be focusing on stop laughing. Start. No.
Talk about the end. And that's all for Crash Course.
See you next time.
Start up.
And then I'll edit it out. Are you gonna stand in front of the ground? Oh no, you're gonna stand right in the middle.
Go.
Great. So cute. Give one thumb down.
Yeah.
Yeah. Thank you. Let me just get that one.
Yeah.
Oh, oops, I accidentally started it.
Hey.
Say hi.
I said hey.